We're happy to have Ofer Aharony from Weizmann Institute to tell us about two-dimensional QCD as a string theory.
Thanks for the invitation. It's always great to be back here at NYU. And so today I'll talk about two-dimensional QCD as a string theory, and this will be based on work that is still very much in progress in collaboration with my postdoc Kundu and my students Sheaffer and L. And the first results of this appeared 2 months ago, and there's plenty more papers to come. So I'll begin with some motivations. So this is a very old topic by now, so I'll explain why I think it's time to go back to this topic. And then I'll describe two different, so the bulk of the talk will be two different approaches to trying to understand two-dimensional QCD as a string theory. One approach will start from perturbation theory, and we'll try to find from there the string dual to 2D massive adjoint QCD. And the other approach will start from a string theory construction for the pure two-dimensional animals, and we'll see why that can always also serve as a starting point for understanding two-dimensional QCD. So almost exactly 50 years ago, Ofer first suggested that there could be a relation between SUN gauge theories and string theory. And in particular, he suggested that if we look at SUN gauge theories in the limit where we take n to be very large, but keeping fixed what we could now call the Ofer coupling, diagonal squared n, or as well keeping fixed on the QCD, then that limit should be equivalent to some string theory where the string coupling goes like 1 over n, so that in the larger limit this string theory becomes decoupled. Now, Ofer's original arguments were mostly based on taking the perturbative expansion in this limit of large n and fixed diagonal squared n, and rearranging the Feynman diagrams or mapping Feynman diagrams to Riemann surfaces in such a way that the diagrammatic expansion could be rewritten as a sum over Riemann surfaces of genus G of something that looks like n to the power 2 minus 2g times some function of this Ofer coupling, and this, of course, is also what we expect to get from string theory, whose string coupling goes like 1 over n. However, these arguments were not constructive. So they don't really tell us, given some gauge theory, what would be the string theory that is equivalent to it in this larger limit. And indeed, it took many years before any concrete examples of this type of duality were found. So first examples were found in some low-dimensional examples, and then following the idea of CFT correspondence, many examples by now are known also in higher dimensions of specific dualities between gauge theories and string theories. And in most of these cases, the string theories that appear on the right-hand side here are just standard critical string theories, but in rather complicated backgrounds that involve extra dimensions compared to the dimensions of the gauge theories that involve Ramon backgrounds and other complications. But in general, we do see that standard string theories are just dual to SUN gauge theories as Ofer anticipated. But even 50 years later, we still don't have any prescription for, given some gauge theory, how to find what is the string theory that's dual to it, or vice versa in some cases. So the question is how to construct string duals for specific gauge theories. Now, one general direction in which we could try to analyze this question is to start from the limit of free gauge theories, where free gauge theories means taking diagonals squared n to 0, but still keeping fixed the fact that we project just onto singlets of the gauge group. So in that limit, of course, we can solve everything we want. We can compute all the correlation functions and so on. And so we could try to ask what is the string dual even to this free limit of gauge theories. And then one could hope that that could then be used as a starting point for adding interactions, perturbatively in the coupling, and then maybe eventually, if one can resum that perturbative expansion, also find the string description non-perturbatively in the coupling constant. But it turns out that even finding the string duals in this limit of free gauge theories is relatively difficult. So in this limit, we don't really expect, in some sense, smooth worldsheets, which we expect to have gluons that are sort of connected by strings that don't really have tension, but that just sort of could follow how the indexes of these gluons are contracted to form singlets. So it should be some sort of tensionless string theory, or something called the string bit model. So we could try to construct models like this, but even these models are not yet well understood, and even for string theories that we do understand relatively well, like the n equals 4 supreme Mills theory. So even in that case, the string theory dual to that in the limit where the gauge coupling goes to 0 is not really well understood. So far, there has not been too much progress on starting from this free gauge theory case and then using that to go to more complicated theories. So what I'll describe in this talk is our attempts to make progress on this question in the specific case of two-dimensional gauge theories. Of course, we're naturally more interested in four-dimensional gauge theories, but two-dimensional gauge theories are useful tooling models that have two big advantages compared to the four-dimensional gauge, which may make this procedure more amenable to computations in this case. So one advantage is that in 2 dimensions, if you just analyze, if you just look at the classical Coulomb force between particles, then the classical Coulomb force between particles already leads to a linear potential between charges. So that's true both for abelian gauge theories and for non-abelian gauge theories in 2 dimensions. So it's if you have some, say, a source and a source in the opposite, say in fundamental and anti-fundamental, then the potential between them grows as if there's a string whose tension is g squared n over 2 connecting them, just already in a free or weakly coupled non-abelian gauge theory. So a confinement in two-dimensional gauge theory appears already classically just from perturbation theory, which is not true in higher dimensional cases where it only shows up as a non-perturbative effect. So in this case, so it could hope that sort of the standard string series with finite tension could arise already at recoupling just from perturbation theory, because in perturbation theory we already see if we have two sources that there is in some sense a string connecting them, in the sense that we have a potential energy that's linear in the distance. So standard finite tension string theory could arise here already just in the perturbation theory, and we'll see an example of how this happens in the second part of the talk. A second big advantage of two-dimensional gauge theories is that in 2 dimensions there are no dynamical gluons, and in general in d dimensions the gluon field has d-2 physical degrees of freedom, and in 2 dimensions it carries no physical degrees of freedom. So the 2D Agnos theory has no physical state if we're just looking at the pure Agnos theory with no matter fields. And in fact, it can be exactly solvable. So this is still a confining theory in the sense that if we look at the potential between external sources, there would still be a linear potential, but it doesn't have any physical states, and it can be exactly solvable, as I'll review in the third part of my talk. And this solution can be recast as a string theory, which was done already 30 years ago, for St. Taylor. And in this case, the dual string theory includes, it's a theory of closed strings, but if you have closed strings in 2 dimensions, then in order to get any finite energy states, then the string has to fold, since there's only one spatial dimension. And there's a specific string theory that's dual to 2D Agnos, then the strings are not allowed to fold, the equations almost forbid that, and that's why in some sense this theory does not have any physical states. If you put in external sources, then you can have a string stretched between them, but you don't have any finite energy strings. So as I'll review, even though one can rewrite this theory as a string theory, finding the precise worldsheet description of that string theory is challenging. However, if we can find a worldsheet description for this string theory, then in principle, it should be straightforward to then add matter fields and find a stringy description for 2D gauge theory with matter fields. So for instance, if we look at the string theory and we add boundaries to the string with Weizmann boundary conditions, that would give us dynamical boundaries. So we know that in the gauge theory side, that should correspond to adding matter in the fundamental representation, namely quarks, which could be either bosonic or fermionic quarks, and then that leads to what's known as, in particular for fermionic quarks, that gives what's called the HEP model. So in principle, if we have a local description of this worldsheet theory, all we need to do is add boundaries, and we would obtain the string theory for the HEP model, which does already have dynamical states because the string can have boundaries, so you can have finite energy strings stretched between these boundaries. And similarly, one could try to add matter fields in the adjoint representation. So matter fields in adjoint representation, again, they could be either bosons or fermions. So in this context, matter fields in the adjoint representation correspond to like extra particles on the worldsheet, or the worldsheet could either continue or it could fold back. So you can have finite energy configurations like this, describing states of like four of these adjoint particles that are bound by these strings. Of course, these matter fields are also interacting among themselves, but if we take the limit that the mass of these matter fields is much bigger than Hooft coupling, then these matter fields should be weakly coupled, so it should be possible to just have a weakly coupled description like this of particles. So again, once we know the string dual of the theory and Mills theory, it seems possible just to add these extra particles and then obtain also the string theories for these dynamical particles. So it sounds plausible that in this way we would have a systematic procedure to find the string duals of all 2D gauge theories. So what I'll describe today is the first step in this program of trying to systematically construct string duals for all two-dimensional gauge theories. And again, I'll do that from two different approaches. But first, are there any questions about the motivations?
I remember some, again, old work on the third part on Young's with adjoint.
Yes.
So you will review what is known and what is.
Yeah. I won't review all the old works, as you said. There are many papers about this throughout the years, but yeah, I'll review the things that are relevant for the approach that I'll try to describe. Any additional questions? Okay, so let's start from the approach of starting from perturbation theory and trying to obtain a string theory from there, using the fact that the confinement force appears already classically. And again, the example that I'll discuss here will be this example of adding matter fermions and adjoint representations, which are very heavy, and namely, if they're very heavy, again, they're no dynamical gluons, so all the particles are heavy, the Young-Mills coupling becomes weak at high energies, so this should give rise to just weakly coupled gauge theories.
Sorry, Ofer, may I ask
Yes.
about second point? Can you remind me, what if one tries to construct in conventionally holographic example, like starts with stack of D1 brains?
Yeah, well, D1 brains first describe the maximally supersymmetric Young-Mills theory, so that
Right.
has lots of adjoint particles and so on, and yeah, so for that we do know the string theory just as usual from holography, and yeah, so that's a two-dimensional example that's known, but yeah, but there it doesn't really have any of these special 2D features. I mean, it's not even a confining theory. I mean, it's some CFT, but yeah, that is. So some examples of 2D theories are certainly understood, but
And it's not easier there than in 4D to go from these conformal examples to
right, yeah. So like in 4D, it's difficult to go further to specific. Like they give, you can just give a mass to all the fields and go to the 2D Young-Mills theory, but yeah, but like in 4D, I mean, it's not really. You really need to do fine tuning to do that, which you lose control over the stringy description. Any additional questions? Okay. So the starting point will just be the action for Young-Mills theory coupled with these adjoint fermions. So we'll have the usual gauge kinetic term, squared, and I'll discuss just SCI gauge theories for simplicity. And then we have some direct fermion in the adjoint representation, or sorry, Majorana fermion, Majorana fermion in the adjoint representation with this usual action. And again, we hope that this will be weakly coupled in the limit where the mass is much larger than the scale set by the gauge coupling or the Hooft coupling. So, of course, in general, this is some complicated interacting theory. We can simplify it by going to what's called a light cone gauge, similar to what Ofer did in his analysis of the Hooft model, which was also 50 years ago. So we'll define light cone coordinates sigma plus minus in the usual way. And it's convenient to choose a gauge choice where one of the light cone components of the gauge field is 0. If we do that, then all the gauge interactions just between gluons vanish. So all that's left of squared is just a kinetic term of A plus. And we can also make a convenient choice for the gamma matrices, in which we'll write the two-component Majorana spinner is to real fermions psi chi. And then after these simplifications, this is the action. So the action takes the following form. So we have this the gauge kinetic term now just includes d minus A plus squared. Everything else has been set to 0. And with an appropriate choice of the Dirac matrices, then one of the fermions is sort of purely left moving, and the other fermion is purely right moving. So one of them has just a D plus in its kinetic term, the other one has a D minus. But of course, they're coupled together by the mass term. It's not Caroline invariant, so there is a coupling between them for the mass term. And then all these terms are just free terms. The only interacting term in this theory is the coupling of A plus and the remaining gauge field that we have freedom to fermions. So which this notation I've chosen, that's just a fermion by Wiener. So this is the fermion current G plus, which couples to the gauge field. So there's just this one interaction term. So this is still a somewhat complicated action, but it simplifies if we do light cone quantization instead of usual quantization. So instead of quantizing it in the usual time direction, we can choose sigma plus to be the time direction. And the advantage of doing that is that only one of these fields, lib psi, has derivatives in the plus direction in its kinetic term, while both chi and A minus, and A plus have only minus derivatives, so they're non-dynamical fields if we do light cone quantization, and they just become auxiliary fields that can be integrated out. So in this light cone quantization, we can just integrate out A plus and chi. Of course, in some cases there are subtleties with doing this light cone quantization when there are zero modes and so on, but here we're talking about a theory where all the fields are massive and so on, so we don't expect any problems with this light cone quantization. And so after integrating out both chi and A plus, we get an action of the following form. So integrating out A plus just gives us a four Fermi interaction, as you can see from joining together this term and that term. So we get an interaction that looks like 1/2 J squared times J plus 1 over D minus squared J plus. Of course, you get a non-local interaction for these fermions, but still explicitly written. And similarly, integrating out chi, you're going to have this D minus here, and it has this linear coeffective psi, so that gives a quadratic term, but a quadratic term looks like psi 1 over D minus psi, which is, I guess, the expected form of a mass term in this light cone frame. I mean, so the Hamiltonian is the momentum in the plus direction, and the mass term looks like m squared divided by the momentum in the other direction. So we can describe this full adjoint QCD theory just in terms of this single real fermionic degree of freedom and the adjoint representation with this non-local action plus the Gauss law constraint that we also get by integrating out A plus, which I won't write down explicitly. Now these non-local interactions look pretty complicated, but they do simplify if one goes to momentum, if one writes it in the momentum variables instead of in position space. So we can define creation and annihilation modes for the fermions. So if one just canonically quantizes these fermions, then one finds in momentum space commutation relations between fermions with momentum k and k prime. Again, this is the momentum conjugate to the sigma minus, which is the spatial direction and the light cone quantization. But the canonical anti-commutation relation just takes this form that positive momentum and negative momentum psi's anti-commute with each other. So it's possible to choose a vacuum where all the positive k's are annihilation modes and all the negative k's are creation modes. So you can choose a vacuum that says that all the psi AB k's annihilated for all positive k's, and then quantize on top of that vacuum. And then so if we do that, then we can write normal ordered version of the Hamiltonian that comes from this action. So the Hamiltonian the Hamiltonian has two pieces, and so there's one piece. Of course, this term drops out if we go to the Hamiltonian language. We have one piece coming from here, which in this Hamiltonian language is k minus k psi k. Operates this from minus infinity to infinity. But yeah, then so here you can normal order it in some way. That just goes from 0 to infinity, and then the interaction term coming from here just looks like k over k squared trace of g plus with momentum k, g plus with momentum minus k, and so and of course as usual. In the light cone frame, I mean, so we have the Hamiltonian that tells us how states evolve in this light cone time, and we have the total momentum of the state, which is just going to be the integral decay of k times the occupation number of the fermions. So that's k psi k. And as usual, in the light current frame, the mass squared of some state is going to be 2 times the Hamiltonian times the momentum. So every state has some positive momentum and positive energy in these light cone directions, and the invariant mass. So if we have some single particle state, then its mass squared will just be the product of this Hamiltonian and this momentum. So we can just expand this current in components and normal order the Hamiltonian to see what's the precise theory that we need to solve. So at the same time I do this beforehand on this blackboard. So if we normal order the Hamiltonian that's written over there, then from the normal ordering of the 2 currents squared, we get some correction to the mass term. So there's some renormalized mass, which is just the mass squared minus 2d almost squared n over pi. That multiplies a quadratic term, which again just looks like the standard term you would write down for massive fermions in the light cone frame. And then there are several interaction terms in this Hamiltonian. So there are interaction terms which have take 2 fermions to 2 other fermions. So those are like 2 to 2 interactions, which come from integrating out the gauge field. I mean, again, either in the T channel or in the S channel. So that gives rise to these specific 4 Fermi interactions. And then there are other terms that change the number of fermions. I mean, so we have this term that takes 3 fermions into 1 fermion. Again, this originally came from exchanging the gauge field between them, of course. So that gives rise to this term. And there's another term that takes 1 fermion to 3 fermions. So this is the full Hamiltonian that we get for this theory in the light cone gauge. And in order to get some intuition for these terms, then probably the most interesting term here in the Hamiltonian is this term. So this term is the term that comes from the T-channel exchange of gluons, and that just gives the Coulomb potential between these fermionic adjoint particles. And you can see that if we just Fourier transform this to position space, so in position space, this would just be written. So the Fourier transform of this in 1 spatial dimensions would just give us something that would look like the integral square times the distance, so sigma 1 minus sigma 2. So it's just the Fourier transform of this just gives us the absolute value of the distance between them. So that gives us the expected linear potential from this T-channel exchange of the gluons. So that's the interpretation of this term. So that's a quick review of how to write adjoint QCD in the light cone gauge.
Let k equal to 0 is some boundary condition.
Right. So yeah. So I'll write down the wave functions in a moment, and then I'll discuss the boundary condition there. So of course, in general, this Hamiltonian describes all the possible states. So far everything I did was completely exact. I mean, I didn't take any limits. So far everything was exact, even for finite n. Now, when we take the larger limit, of course, we expect that only planar diagrams will survive out of this full perturbative expansion that follows from this Hamiltonian. And related to this, we expect that states made from a single trace of these fermionic degrees of freedom will decouple from the states that are made of multiple traces. I mean, so in general, if we start with some gauge invariant state, that in general it would be some combination of a single trace of a product of fermions, 2 traces, and so on. But in the larger limit, the multi-trace states decouple. So if we're looking at large n, we expect to have particle-like states, which would correspond to the single trace combinations of these fermions. And if you have a particle state, a priori, of course, it could have any light cone momentum, but we can always boost the momentum in the light cone direction just so that it's equal to 1. Right? So we can always choose to look only at states that have p equals 1. Of course, the states that have any other value of p are just related to that value boost. So the way that a generic and the states could be either bosonic or fermionic, depending on if they have an even or odd number of these psi's. So for instance, if we want to look at generic bosonic states in the large limit, then they would have the following form. I mean, so they would be made out of an even number of these adjoint particles, which would be 2, 4, 6, and so on. And so the wave function has contributions from different numbers of these partons, and the contribution from n partons will be some wave function as a function of these momenta. So the momenta all go from 0 to 1, and since we chose the overall momentum to be equal to 1, then they have to sum to 1. So we have some delta function that the sum of the momenta has to be equal to 1. And then we're going to have some wave function as a function of these n different momenta, which multiplies just a single trace state with the appropriate creation operators, psi minus k1 psi of kn, acting acting on this vacuum that I defined before. So this is in the larger limit. Again, we can only consider the single traces. We don't have to consider mixing with multiple traces. So the problem of finding the spectrum is just the problem of finding all these wave functions phi n that are eigenstates of the Hamiltonian. So we just plug this into the Hamiltonian and find the eigenstates. And the boundary conditions, as Sergei mentioned, so we have to impose boundary conditions that the wave functions vanish at zero momentum. So again, this is similar to the HEP model. One can show that these are the correct boundary conditions such that the Hamiltonian is self-adjoint and gives a well-defined problem. So they obey this, and they obey, and by construction, it's obvious that these phi n's are cyclic in the case because the cyclic fermentation gives exactly the same state. So those are sort of the boundary conditions, and with these boundary conditions, we have to solve for what the spectrum is. So that's the setup. Now, unfortunately, finding exact solutions to this is still very complicated, even when we get to this larger limit. So solutions are known for low-lying states. So low-lying states are basically non-relativistic bound states of these massive fermions. I mean, so for the low-lying states, the mass terms dominate, and one can find states that just look like these fermions moving in this linear potential. So sort of similar to what people here analyze in this zigzag model, but now with just a non-relativistic massive fermions rather than massless fermions. So the low-lying states can be found. I mean, so they have energy sort of slightly bigger than the number of protons times the mass. But what we want to describe is states that have what is the high energy spectrum of this theory, and that turns out to be more complicated. I mean, so we want to describe states that have an energy much bigger than electron energy, much bigger than this mass squared, and that turns out to be more complicated. So far, well, what can be solved analytically is simplified versions of this model. So one simplification one can make is to drop all the terms that change the parton number. So if we drop the parton number changing terms, then there's a separate wave function for each number of partons. I mean, so the terms with n fermions don't mix with terms with a different number of fermions. And so then, if we look at the sector just of these wave functions, just of n partons, and we go to very high energies, then the simplest way to get high energies is just by taking this Coulomb term to be large. So in that limit, the states, so in this limit, the states are dominated by states that diagonalize this Coulomb term. Now the Coulomb term is pretty complicated in momentum space, but it actually takes a very simple form in position space. So if we just do the Fourier transform of this Coulomb term to position space, then it becomes just g mod squared n over 2 times just the sum of the distances between. So if I do x is sigma minus just to save, and so it just becomes the sum of the absolute values of the distances between these adjoint particles. So we have n of these particles. The Coulomb term just becomes the sum of the linear potentials between them. So we have this picture of the states really as I drew them before. I mean, so again, but now this is derived rigorously from the perturbative Young-Mills theory or perturbative QCD theory. So the energies are just given by the sum of the lengths of the string. So in this limit, it's easy to find a complete set of eigenstates of these Hamiltonian. I mean, essentially, it's just like n copies of the 't Hooft model at very high energies. I mean, so you get like the masses squared are just sums of n independent Regge trajectories, essentially. So that's the picture that one gets in this limit. Now, naively, if one then assumes that this approximation is good for the full spectrum, then it looks like one would get a Hagedorn spectrum coming from joining together all these Regge trajectories. With a Hagedorn temperature that's of order this string tension scale g mod squared n. But in fact, that turns out not to be true, because in order to get the Hagedorn entity, you really have to have lots of these segments. Once you have lots of these segments, then also the mass terms become important, because the mass terms always contribute at least n times the mass, and then the high mass limit this becomes important. So the actual high energy spectrum comes from balancing this Coulomb term with the mass term that's written over there. Now, the actual answer for the spectrum of this theory in the large mass and very high energy limit, it's actually known from computing the thermal partition function at one loop. So from the thermal partition function, we know that the density of states in this theory does have a Hagedorn-like behavior, but it's a Hagedorn-like behavior not at the scale of the string tension, but actually at the scale of the mass. I mean, so one gets a behavior that's like this with some algorithmic correction. So this is what you find from the one loop partition function, that this theory should have Hagedorn-like behavior with that Hagedorn scale of the mass, and we can show, although we haven't rigorously proven yet, that this is precisely what you get by just putting together here the density of states coming from these different string segments plus the mass terms. I mean, even when ignoring
So what are the M, capital M?
Yeah, sorry. So the spectrum. So we have here a spectrum of different eigenstates of this Hamiltonian. So here, the Hamiltonian. So 2h is just the mass squared of our particle states. So each eigenstate of the Hamiltonian we identified with some particle state whose mass is the square root of 2 times h. And then I'm just asking what's the density of these particle states of the meson. So of course, if this was in the TOOF model, which we also get here for n equals 2, then we just have a single redshift trajectory, and then of course this density would just be linear. But once we have lots of these redshift trajectories, then together they give rise to this Hagedorn-like behavior. And the one loop partition from the one loop thermal partition function, one can show that the Hagedorn temperature is actually given by something of the order of the scale of the mass. And what we're still in the process of finishing to do is to show that this is indeed what you get by just looking at the spectrum of this theory of high energy and balancing the contributions from these Coulomb interactions with the contributions from the mass. But our hope is that once one does that properly, it will indeed give precisely this type of behavior. So that's one concrete question in terms of sort of solving for the density of states of this theory at high energies from this Weizmann Hamiltonian.
But the expectation is that for all the other terms can be dropped. That would be the non-trivial. The non-trivial claim is that all the terms can be dropped, but for this linear potential.
Well, no, it's not precise, but the claim is that gives at least it gives a good approximation to the spectrum. I mean, the other terms are not negligible, and of course you do need also the terms that mix the different fermion numbers and so on. But the claim is, which again we haven't finished proving yet, but we think that's what's going to happen, is that the other terms are not going to qualitatively modify this Hagedorn type of behavior. They'll just change the details of the precise spectrum, but the density of states, they don't change the leading order density of states.
So this means the technical claim would be that the spectral density would be the one you wrote with the right coefficients you can compute from one loop calculation. Just those
exactly.
terms.
Right. So that's in some sense, again, that's already known from the 90s, that the one loop computation gives you that there is a Hagedorn instability precisely at this temperature of the mass over logarithms with that. So we know that that's the density of states. The only challenge is to really see how the spectrum recreates that exponential density, which is not far from obvious from this way of writing this theory of adjoints with four Fermi interactions. But we expect that will happen precisely by balancing these Coulomb contributions, which again, if they were on their own, then they would just give a Hagedorn density of states, but they are at this other scale, G n squared n, but because they have to be balanced by the mass terms, then the leading and so for each energy there's sort of a value of the parton number that sort of maximizes the interplay between getting a large density of states from these n different strings, but also getting a contribution to the energy from n times the mass and so on. So it has to balance these things and find which parton number maximizes the spectrum at a given energy, the density of states at a given energy. And the claim is that when we do that, we reproduce this density of states.
But do you expect to reproduce it with the correct coefficient in front of the
Well, we
loop?
hope so, but we haven't finished the computation yet. We're not sure if that will work in this approximation or if the corrections will maybe change the coefficient. So yeah, that's the part we haven't.
The argument of the log probably will get shifted, right? So that's
well, okay, it's just like up to a coefficient, then
basically the leading log part
Right.
you expect.
yeah,
is that
exactly,
right?
right. Yeah, indeed. So that's what we hope to be able to see from this analysis of the spectrum.
And what is the argument for that? For this expectation? Is there?
Well, we don't have a good intuition. I mean, in some sense, the intuition is just that this Coulomb term is the only term here that can sort of grow indefinitely, because this K1 minus K4 can be arbitrarily large, while the other terms are sort of they're bounded because all these K's are positive and so on. And so they don't. They look like they should be less important at high energies, and so but that's just a hand-waving argument. And again, we still need to finish all the details and see that it really works.
Your convention, where is the supersymmetric point?
Yeah, so there's a right. So this theory indeed one interesting property that it has that's sort of accidental from this point of view of the Hamiltonian that we wrote down is that it happens to be supersymmetric, I think, in this normalization for m squared equals g of
That's
s
why
squared
the
and
mod is
pi, I
zero.
think. So there's some specific value of the mass where this theory happens to have a supersymmetry, and there's a degeneracy between all the bosonic states and all the fermionic states. But that's,
But
yeah,
does it
that's far
happen
from clear in this language.
does it happen to?
We're certainly analyzing it at the very massive limit where it's very far from the
I see.
supersymmetric point.
I see.
But yeah, but
I was
indeed,
hoping it will help you to understand this balance between the mass term and the potential.
yeah, right. No, but it doesn't seem that. I mean that balance is really just for very high energies, for high masses. Sorry. Once we lower the mass, then certainly the parton number mixing terms will also start becoming important, and so on. So I don't expect that to be a good approximation when the mass is of order or the gauge field. Yeah. So one thing we're trying to do is to analyze the spectrum. The thing that we'd like to do even more than that is to try to take this light-cone Hamiltonian and try to see if we can rewrite this as a Hamiltonian of the string worldsheet theory. So this is almost like it's the Hamiltonian of the string worldsheet theory. I mean, we have the kinetic term that corresponds to these massive particles on the worldsheet. We have these tension terms describing the tension. So what we'd like to do is to just take that Hamiltonian and rewrite it. And again, in this larger limit, then if we focus on the single trace states, and that just describes the evolution of a single string. So we'd like to take that Hamiltonian and rewrite it as some string worldsheet theory to give us the string dual to this massive adjoint QCD theory. So far, we don't know how to do that and get a local action for this string worldsheet. I mean, that's not clear, but we hope that there is some way to rewrite this Hamiltonian as a local action on the worldsheet. And again, that would be a constructive way to find the string dual to this massive adjoint QCD. So yeah, but that's the state of the art so far on this approach. So are there any more questions on this approach?
A priori, do you have a reason to expect there to be a local worksheet description?
Yeah, that's a very difficult question. Yeah,
Apart from
even in
this,
usual
we're
critical
not-
string theory, it's not obvious to me what distinguishes the theories that have local
Yeah.
worldsheet actions from those that don't have local worldsheet actions.
You just go to
I
the
mean, that's
page
sort
and
I mean, you know, at Hooft's original arguments of resumming the perturbation expansion do suggest that the action should be local on the worldsheet in the larger limit. But mostly based just on those arguments, I would expect that there should be some local description of the action on the worldsheet, but I don't have strong arguments that.
But when you asking that, do you have in mind some local CFT like description?
Well, CFT, I don't know. I mean, probably it would be easier to do this in light-cone gauge. I mean, since I'm starting from a light-cone gauge Hamiltonian, and in light-cone gauge it doesn't look like a CFT, but okay, but it would still have whatever symmetries it needs to have in this light-cone frame or whatever. So.
Because in principle one can just study scattering the difference on the sector with a flux tube.
That's right.
And the test matrix at low momenta
Yes.
looks
Yeah.
normal. It's
Right. Yeah, right. So that's right. So another approach to try to get the same string action would be to start from this theory in the presence of a Wilson line in the fundamental representation. So that already describes an infinite string, and then one could describe the excitations of these particles on top of that. So yeah, so indeed that's sort of a different limit of the same string theory, and indeed that approach should also enable one to find the sort of, well, at least sort of from top down from low energies to find what is the action of this worldsheet. So yeah, all these different things should give us clues as to the right way to construct this worldsheet. But yeah, I agree that nothing guarantees a priori that there should be a local way to write it down, but we hope that there will be. Any more questions about this part?
Just a basic question. So in this order, like in any other two-dimensional theories, you also confine what is not confined in four dimensions, like all these single, the adjoint matter, etc.
Yes. Well, they are confined also in four dimensions. So the ones that are confined also in four dimensions. So yeah.
Well, if you have
here all these
sources
things
in
are-
the fundamental, but
Yeah. Yeah, right. You mean that they can be screened? Yeah. Right. Yes. So So here, here also, I mean, the sources in the adjoint can certainly be screened by these dynamical fermions. And so in that sense, it's the same as in four dimensions. I mean, the surprising thing about the Studi theory, if you remember, is that if you take the mass to zero, then actually it turns out that these adjoint particles can even screen sources of the fundamental representation. So that's highly non-trivial, but yeah, but that's an opposite limit from the one that I'm studying here. So they don't have anything new to say about
And the limit,
about that.
indeed, the limit done by Kutuzov in
Right,
93.
yeah, so that's the opposite limit where the adjoint is massless at the end. They're gauge very differently. I mean, there the strict tension goes to 0. There's really no confinement. So yeah, that's a different. That's a completely different limit. Okay, so if there are no more questions, then let me switch gears now to the third part. So the third part will start from just the pure 2D Yang-Mills theory, and I'll remind you of what's known about finding a string theory dual description for that theory. So in this theory, the action is just this square term. And this theory, as I said, has no dynamical degrees of freedom, and in fact, it can be exactly solved. So if you put this theory on a circle, then the only dynamical degrees of freedom comes for the holonomy of the gauge field on the circle. So the eigenvalues of the holonomy are gauge invariant, and it's easy to quantize the resulting Hamiltonian. And it turns out that there's one state for every representation of the gauge group that can be thought of as created by Weizmann left representation on this circle. So it's easy to solve exactly for the spectrum of this theory on the circle, and the energy eigenstates are just G(L) squared over 2 times the length of the circle. So the circumference of the circle is L times the second Casimir of the appropriate representation. And of course, from here, one can easily get the partition function on the theory on a torus, but in fact, it's been shown that by gluing together these cylinders, one can also compute the partition function of this theory on any genus G manifold. So if you put this two-dimensional Gauss theory on any genus G Riemann surface, then the partition function, well, it has one piece that's already there on the torus, so which is just the G(L) squared times the area times C2 of R. So that's what you would get if you just theoretically identify this cylinder. Then obviously you would have that contribution giving you the partition function of the theory on a torus, where the height of the cylinder times the length would just be the area of this torus. So for a torus, that would be the full answer. If you're in a Riemann surface of a different genus, then there's an extra term, which is the dimension of the representation raised to the power of 2 minus 2g. And it turns out that this is the exact answer for the partition function of this pure Yang-Mills theory. And similarly, one can compute exactly also expressions for the expectation values of any Wilson lines and so on. So I won't review that here. Now, what I'm interested here in is describing the string theory dual of this 2D Yang-Mills theory. So for that, we want to take this limit of n goes to infinity, keeping fixed G(L) squared n, which I'll denote by lambda. So the first question is, which representations survive here in this partition function in that limit? So this was analyzed by Gross and Taylor more than 3 years ago by now. And what they showed is that the representations that survive are of the form that they involve Yang tableau that have n boxes. I mean, so that they appear in the product of n fundamentals, where this small n remains finite in the large n limit. Or one can have representations which have sort of until the anti-boxes. I mean, so that they're the complement of some of columns of height n with until the additional Yang tableau. So in other words, these are all the representations that we could get for a product of n fundamentals and until the fundamentals, where these n and until the remain fixed in the large limit. So they show that these are the only representations that survive in the sum when you take this limit. And then they show that one can just rewrite this partition function as a string theory in the sense of having a genus expansion with the string coupling being 1 over n, and they show just by combinatorics that one could rewrite that genus G partition function as a sum over small g, which is going to be the genus of the worldsheet of the string now that describes this 2D Yang-Mills theory. And then there's a sum over integers n and n tilde, which correspond to these. So that comes from this sum of representations. So it counts the number of boxes in these Yang tableau. And if you look at the terms that have n and n tilde boxes, then they correspond to worldsheets, which cover the space-time as n times with one orientation and n tilde times with the opposite orientation. I mean, that's as expected from the fact that they come from a product of n fundamentals and n tilde anti-fundamentals, and they correspond just in this stringy language to strings with opposite orientations. So you have this contribution, and then on top of that, there's a sum over some configurations with special points on the worldsheet, which give rise to some polynomial terms in the area. So again, I mentioned it. And I mean, in this pure Egg-Mills theory, the partition function only depends on the area of the space-time, and it doesn't depend at all on the shape, just on the area. And then there are some specific coefficients multiplying these terms. So this looks like the expansion that you'd get if you had some string theory with the string coupling equals to 1 over n, and with a string tension, which is lambda over 2. And then if you have these configurations with n string lining the spacetime with one orientation and until the strings lining around the spacetime with the opposite orientation, then that will give you precisely these contributions to the action. Now these extra terms again, which come up just from rewriting that expansion in the large limit, they were interpreted as describing mappings from the world sheet to the target space that have some specific types of singularities, like branch points and some other singularities that I'll describe. So each of these branch points gives some factor of the area essentially because it can sit anywhere in the space-time. And then there are these some specific integers multiplying each of these terms that are interpreted as sort of countingly independent maps of this form. So this just comes from expanding that partition function in the larger limit, and indeed it looks like we have a string theory here that describes this 2D Egg-Mills theory, and that in some sense counts maps from some worldsheet to a spacetime, but again, where these terms come from worldsheets that map the spacetime again n times with one orientation until the times with the opposite orientation. Here I wrote the full partition function. Of course, the connected partition function coming from a single string will just be the log of this, and so that we give the contribution of single strings to this partition function. But the question is, can we get this this expansion from any local worldsheet action that will tell us which string theory it is that actually gives us expansion? So of course it looks like a string theory, but the question is, what is the string theory that indeed gives us this expansion? And that turns out to be much more complicated. So if you look only at worldsheets that have a single orientation, so if you look only at the contributions from what's called Carroll representations that only have product of fundamentals and no anti-fundamentals. So if you look just at this sector of the theory, then that is much simpler to describe by string theory, because here all the worldsheets have the same orientation, and you can show that in this case the configurations are just given by holomorphic mappings from the worldsheet to the target space. And then there are many known topological string theories that just sum over holomorphic mappings from the worldsheet to the target space. So if you're just interested in this sector, then that's sort of easy to get from a worldsheet. So there are many descriptions of that. I mean, the first ones were it's more in
Sorry, what does it happen with these terms in this case? In the chiral case, what does it happen with these extra factors there?
So here you just drop all these extra factors. You should just, out of the sum, you only take the terms that have n tilde equals 0. You don't take all the other terms. And those terms can be derived just by counting holomorphic mapping. So they correspond to relate just mapping worldsheets with the same orientation. So this part of the partition function, that's easy to get from a local worldsheet action. And again, because you do need to just sum over holomorphic mappings. And there are many ways to do that. Again, it was first done by Weizmann and Gulam. I mean, then there were just by Rafa, and there's a recent work also by Shotokomatsu that gives some other way to describe this. And so there are many different ways to count holomorphic mappings.
So this truncation in terms of original gauge theory, is there?
Yeah, I don't think it has any nice picture. I mean, it's really, in terms of the sum of representations, I mean, yeah, you're just keeping those representations. I mean, first, beyond infinite n, it's not even well defined. I mean, how to distinguish them. But in the infinite n limit, it makes sense to drop all these anti-fundamentals and keep just the fundamentals. But yeah, I don't think it has any.
Is there a
direct,
direct turning on Q deformation in the original theory and taking a specific limit of the Q parameter? That's what we write the topological.
Yeah, that's a good question. Yeah,
to the Q deformation of the animals and take a limit of the Q parameter.
Yeah, that's a good question. I'm not sure. Yeah, I don't know any simple deformation that keeps only those things. Yeah, it's possible, but yeah, I don't know if that's possible.
And these different prescriptions, are they in some sense equivalent, or it's not clear?
That's an excellent question. I mean, I don't think it's known. I mean, yes, of course they're equivalent in the sense that
they produce this answer, but
same
the moment
formula.
you
But yeah, but are they locally equivalent, for instance, on the worldsheet? Probably they're not locally equivalent. They may be the same theory, but in different gauge choices and so on, and there's some extended symmetries and so on. I mean,
so it may be that only one of them or none of them is a good starting point for
that's right.
including the
Indeed.
others.
Yeah, so yeah, our claim will be that none of them are good starting points, and we'll start from someplace different indeed. And so, yeah, but what we'd like to describe, of course, is the full theory that has also these n and tilde, because like our first goal would be to describe this open string sector, which would be the tuple when we had boundaries, but already when we had boundaries, then of course the worldsheet, the evolution of these things would look something like this, where the worldsheet changes orientation all the time. I mean, so it's only not described just a worldsheets of one orientation, but already to describe that tuple model, you certainly need the states with both orientations. So it's not enough for us to do that. So we need some prescription to sum over all these different mappings. So there have been various attempts to do that. I mean, so Willem had some suggestion, and there's also a suggestion by Perturbation. These suggestions were completely explicit. Basically, what you need when you include these mappings that have both orientations, you don't sum just over holomorphic mappings, but it can be shown that you still sum just over extremal area mappings. And so, of course, holomorphic mappings are a special case of extremal area mappings. But in some cases, you need mappings that are not just minima of the area, but that actually maximize the area. For instance, if you want to look at configurations that are connected but have both types of orientations, say with n equals and tilde equals 1, then it turns out that the two orientations are connected by what looks like some sort of orientation reversing a tube. I mean, where they're sort of connected with an opposite orientation by some zero size tube like this. And so you can imagine like closing this into a sphere and getting a mapping from a sphere to a sphere that covers it twice with opposite orientations. But of course, this is not a minimal area mapping, because you can always certainly just geometrically just increase this tube to have a finite size, and that would decrease the area. So obviously, this is not a minimal area mapping, but it's still an extremal area mapping. And these extremal area mappings, whether they're minima or maxima, they all seem to contribute to this sum that we have here. So in order to describe the full theory, you have to include also these weird mappings that we don't usually consider in string theory, which are maximal area mappings and not just minimal area mappings. And you have to be allowed to have also these types of singularities, which are zero size tubes connecting two different orientations and other types of singular objects like that.
So just to be sure, so the mathematical precise statement is this W numbers are contained in extremal mapping.
Aren't what? Sorry.
It's the precise statement is that the W's are precisely contained in extremal mapping.
Yeah, so I'm just going to make the precise statement about this. So the precise statement found by Weizmann is that these W's are precisely equal to the Euler number of the moduli space of extremal area mappings. So the mappings you need to sum over is just these extremal area mappings, and each class of extremal area mappings with some topology is supposed to contribute by the Euler number of the moduli space of these mappings. Because if you have a mapping with some of these tubes, then the moduli will be like the positions of these tubes, and you have to take the Euler number of that moduli space, and then it's been shown that that's equal to these numbers. So we have to find a string theory that computes for us the sum over extremal area mappings of these Euler numbers, and so that's the essential goal. So Hojava wrote down some putative local worldsheet action that's supposed to count them, but if you actually try to in detail use this action to compute things, you get things like 0 over 0 everywhere, so it's difficult to make sense of. So what we did is we wrote a generalization of Hojava's theories, so he wrote some analog of like an Amogoto type string to describe these things, and we're working in a polytope-like formulation where we have also a worldsheet metric. So let me just briefly describe. It's the action that we use that we claim computes this sum over extremal area mappings. So the action is written in 2 dimensions plus 2 extra fermionic coordinates. So we use a superspace to write it so that we can localize just on these extremal area mappings. So the variables, so we have this superspace with 2 fermionic coordinates. The variables that we use are just these x mu's, which are the mappings from the worldsheet to the spacetime. So mu goes over 0 and 1, and you just get a 2-dimensional string. So this has some fermionic coordinates. They have fermionic partners, and there's an extra bosonic partner mu. And then we also have of the big X the superfield, and the small x the actual components, and then similarly there's a metric components, just HEP, and then there's some fermionic component of that, and the R component, the R component, and so on. And the action is essentially just some superspace version of the usual polytope action. So we have an integral over the spatial coordinates and over these fermionic coordinates of an action which in superspace is just like the usual polytope action. So it's the x mu times the metric times the x nu. So this is just the usual polytope action, but now in superspace. And then there's an extra term you need to add, which is the following form. So these are x mu times k nu of x, which is the extrinsic curvature of the induced metric, as the big bar of x nu. So what we claim is that the path integral over these x's and the metric with this action computes that partition function. Now, formally, the way to prove this is that you can show that in the step of surface space you have localization to just as often happens in these supersymmetric actions, you localize just to the classical solutions of this action, which in this case are precisely these extremal area mappings. So you can show that the solutions. So this action, the usual supersymmetric localization, localizes precisely to extremal area mappings. Now, if we just had this first line, then it would localize to extremal area mappings, but then we'd have a moduli space of these mappings, and we'd have fermionic zero modes that would just lead to the partition function vanishes. So then we need to have this extra term to soak up the fermionic zero modes, and we can show that. So when you do have a moduli space of mappings, this second term exactly soaks up the fermionic zero modes in such a way that it turns them into the Weizmann number on the moduli space in a similar way to what happens in various topologies. Theory. Yeah, so KNU is the, so this is the extrinsic curvature of the induced worldsheet, of the induced metric. So it's the extrinsic curvature of the induced metric, and so it's some derivatives of these x's.
So Gauss-Bonnet theorem reproduces the other characteristics.
I mean, you have to work a bit to show that on the moduli space, this thing just reduces. I mean, so it sort of takes each four fermions and replaces them by the Riemann tensor, and then once you have that, then you just get a product of Riemann tensors that gives you the other.
Sorry, what do you mean extrinsic curvature when induced metric?
Yeah, so there's some specific formula, and just the usual formula for the extrinsic curvature tensor.
Extrinsic curvature, that's usually.
This is to what? I mean, you have a two-dimensional surface.
Yeah, so I have two-dimensional surface mapping to a two-dimensional surface, and so extrinsic in the sense of the space-time. I mean, so
because typically it's proportional to the normal.
So in 2 dimensions, this extrinsic curvature actually vanishes at any regular point. I mean, so at any regular point of this mapping, this is just 0. But whenever you have a branch point or one of these zero-sized tubes, then it is non-zero. So this term actually turns out to be a sum over delta functions at either branch points or at these singular tubes.
But in high dimensions, it would be what?
Well, in high dimensions, I don't know, but in high dimensions, of course, it's going to be very complicated. But in 2D, this really is. I mean, the curvature is all localized. I mean, just at these special points, either branch points or these zero-sized tubes, and this becomes a sum over delta functions over them, and then from there you get some non-trivial induced metric.
Do you mean extrinsic curvature or its usual curvature? I'm a bit confused about the meaning of the word.
Well, just not the worldsheet curvature. I mean, so this has space-time, and these are not worldsheet. So that's what I mean. The intrinsic. I mean, there's the intrinsic curvature which just follows from this metric H. So I mean, not that, but just the curvature in space-time of the induced metric.
So there is
Induced metric? Yeah, curvature of induced metric.
It's a
Ricci tensor?
That's Ricci tensor of induced metric. I think that's what.
I think that's.
It's usually it's intrinsic curvature.
It's an intrinsic.
That's why you're reproducing with Gauss-Bonnet the other characteristic. You need the bulk error.
So formally, if you just plug in this action and compute the path integral, just localize these external area mappings, and you get precisely the answer you want.
But sorry, this action, the first term looks like Polakov action.
That's right.
But the whole thing is not conformal because that second term, is it a CFT?
Well, here I didn't do any gauge fixing yet. Of course, it's not supposed to be conformal, but yeah, if you want to first, you can gauge fix this to conformal gauge. I mean, so take this H to be delta IB or whatever, and then of course you get conformal invariance. I mean, the third action is completely diffeomorphism invariant. In fact, it's super diffeomorphism invariant. So.
But the second term, well, it's localized.
Yeah, so this term is not manifestly super diffeomorphism invariant because of these explicit derivatives and so on, but you can show that it is still, because of properties of this extrinsic curvature, that it is still super diffeomorphism invariant. But it's certainly invariant under the usual diffeomorphisms, and so obviously, that's enough so that you get conformal invariance if you choose to go to the conformal gauge. And so we explicitly evaluated it in many examples. So in the last few minutes, let me just mention that. So formally, this action reproduces the sum over the extremal area mappings with the correct weights and so on. But the big problem is that usually these spaces of extremal area mappings are highly singular spaces, and the question is, do these formal expressions really correctly reproduce the answers that we want even in these singular spaces? So already, if you just look at the space of holomorphic mapping, say from the sphere to the sphere with a double cover, then if you have a double cover from a sphere to a sphere, then that covers the space-time sphere is covered twice by the worldsheet, and then it turns out that there are exactly 2 branch points where when you go around them, the 2 sheets of the worldsheet are exchanged. So the moduli space of these mappings, for instance, looks like S2 cross S2 mod Z2, where the Z2 just exchanges these 2 branch points, and then this space is singular at the point where these 2 branch points exactly are on top of each other. So there's a singularity there, and a priori it's not clear how to define the Euler number at that singularity. So what we have to check is that our action reproduces the correct completion of the Euler number to these singular spaces that is consistent with the Yang-Mills theory. So that
It is different when you restrict to holomorphic mappings.
no, this is actually there even for holomorphic mappings. If it's already there, you encounter these types of singularities. And
No,
so
yeah,
that's
when you restrict to holomorphic mappings, does it agree with any of the earlier proposals? It's,
yeah, so that's a good question. Yeah, not manifestly. Yeah, so it's not right. It's not so clear.
it's different.
And yeah, it's, of course, it's only many of these fields on the worldsheet are not dynamical and so on. I mean, yeah, you can always imagine that integrating on some fields, redefining some other fields, maybe you can map it to one of these other formalisms, but yeah, it's not manifest. Yeah, so there's a specific prescription for how to deal with these singularities, which is essentially just to throw them away. I mean, throw away all these singular overflow singularities and compute the other character of the resulting space. So that gives the right answer, and we showed that our string theory, at least in some examples, reproduces precisely that prescription for these types of singularities. Then there are the more subtle singularities, which are the singularities that involve these orientation reversing tubes. So for instance, if you have a mapping from the sphere to itself with n equals until n equals 1, then yeah, then you have one of these orientation reversal tubes, and then it sort of smoothly joins together to cover the sphere. I mean, if you imagine sort of the rotation curve of this thing, I mean, with a 0 size orientation reversing tube here. So of course, these mappings are singular mappings in the sense that if you look at the worldsheet, so the worldsheet sort of half of it maps to the spacetime with one orientation, half of it maps to the spacetime with the other orientation, and in the middle, there's this whole circle on the worldsheet that just maps to a point in spacetime. So obviously, this is a singular mapping, and again, it's not completely obvious how to compute the contributions of those types of mappings. So we introduced some specific way to compute the path integral by some sort of constrained instant-on procedure, where these singular mappings are sort of resolved to finite-size folds whenever you have a finite parameter, and then we showed that for the finite-size folds, we do know how to compute the action, and then take the limit, and we showed that in the limit you do get the correct answer. But of course, there are many subtleties. We haven't proven it in complete generality, but so far the examples that we studied look like this does work.
Very general question. So this kind of not ambiguity, but this prescription you need in order to do this is somehow related to the ambiguity you have in the Rojava regulation. I mean, this is the polyactual.
Yeah, it's not. Yeah, I don't think it's not directly related to that. I mean,
but you also have the undeterminacy there.
Like that indeterminacy was also there, but yeah, but there the extra indeterminacy. I mean, there are even without those singularities, there was already zeros appearing from various other places. So it's not even we couldn't even make it well defined to even ask that.
So you cannot identify that the always come from singularity.
Right, but I mean, I think this answer would probably be the same in his formalism if we could make sense of it precisely. But yeah. I mean, our formalism is supposed to be sort of just a variation of that thing that does make sense and correctly deals with all the zero modes and such. So we claim that also these other singularities are correctly dealt with in this approach, but we haven't checked it in complete generality yet, but just in some examples. And yeah, and I should mention that this actually sort of this only describes the limit of lambda equals to 0 of the worldsheet, so that limit is already rather complicated. I mean, even if you take lambda to 0, you still have to correctly reproduce these numbers for I equals 0. That's already a highly non-trivial sum over mappings. So far we checked that we can correctly reproduce in at least some examples the sum of our worldsheets that corresponds to the zero coupling string theory. So let me end just by describing some of the future directions that we're currently working on.
Can you
Unless there are
what's the
questions
geometric
before that.
meaning of the limit in the worksheet? Does it have understand the string as purely geometric, just complete geometric stuff, essentially?
Yeah.
Yeah.
I mean, in this time equals 0 limit, then the action is also invariant under any space-time diffeomorphisms. But yeah, once you go to finite coupling, then it's not invariant under any space-time diffeomorphisms anymore, but only under the area preserving ones. So that.
Yeah, but this one says like the action is actually on the super diffeomorph, like
On the worldsheet, not in space-time,
so that there is no
so there's no
meaning to this.
Right. It doesn't seem to. Well, we don't know. not clear what that means.
So if
And
with
it's
this
a
action, if I
mathematical trick to do this localization, but yeah, I'm not sure if it has any meaning beyond that.
so if I go say to conformal gauge,
Yes.
because it looks like some Polakov action plus that.
Yeah, but it's a Polakov action in superspace. I mean, so if you take the lowest component of that, then that would be like the Polakov action, but the action is sort of the top component of that. So as usual by localization, I mean, so the localization localizes it to the solutions of the bottom term, but the action is then just 0. I mean, you don't get any non-trivial action. So we have to add some other term that would be like the bottom component of this in order to get the area term, if you want to get for non-zero coupling. So the first.
So this kind of singularity, does it help if you add some Q exact terms to the action? Does it help the regular singularity?
Yeah, we haven't been able to find. Yeah, maybe we didn't.
But there's
finding
no
it turns out it's
term.
not. It's not. I mean, yeah, we don't know how to. Yeah, it's not clear how to do that. I mean, like in the case of mappings from the torus to the sphere, for instance, then you have an extra integral, say, over the modular space of the torus and on the worldsheet, and then for any finite value of this tau, then also that regularizes these singularities. I mean, so that sort of acts like some constraints on that parameter. But the actual contribution turns out to be from the limit that tau goes to I infinity. I mean, and there it really becomes a singular fold. But for any finite value of tau, you do have regular mappings. I mean, so in some sense, in the full path integral, you do have also the regular mappings, but the final contribution localizes to precisely the singular mappings. But again, as long as we can single value it in a single value way to compute what would be the result of these singular limits, then we're happy with using this action. Yeah, of course, it would be much better if we could write an action that would not be singular at all in these limits, but yeah, that we don't know how to do.
So
but at least we find it as a limit of non-singular configurations. So that's the best we were able to do.
But in this prescription so far, how can you be sure that your prescription is giving you the correct result? Is because you know the W numbers already in those cases?
Yeah, exactly. Right. Yeah, so it's just not
changing
in this case, and in these cases it's only we just map to the right W numbers and see if they get the correct answers exactly.
How to see that there is no like Polakov anomaly here?
Yeah, so that's sort of obvious in this superspace. I mean, you have sort of exact cancellation of bosons and fermions and so on. I mean, this is sort of like a topological string theory in that respect. I mean, so we really don't know how it's almost everything cancels between bosons and fermions. It's kind of a unitary theory, and you really get negative contributions from the fermions, positive ones from the bosons.
So in the conformal gauge, is it some non-trivial CFT, or it's really kind of everything?
Well, in the conformal gauge, if you have to flat space, yeah, no, it's still not a non-trivial CFT. Yeah, I mean, like when you get things like this, and this BMU really acts. If you expand this in a component, this BMU acts like a Lagrange multiplier that enforces the Navier-Stokes equation. I mean, so you have to have like BMU box X mu and so on. I mean, so in that sense, it's like what you might call a rigid string theory, where you really impose plus a square term that comes from here. But then, if you expand it in components, it looks more like what's called a rigid string theory, where you have these boxes squared and so on. And yeah, but it doesn't really look like usual polyglot. But again, that's what it seems that you need in order to reproduce the correct answer. So there are many future directions that we're trying to follow, and so the two that we're actively trying to follow now is first to find a generalization of this to finite gauge coupling. I mean, where we need to add also some area term to this, and we're still not sure if we can add an area term while still preserving this full super diffeomorphism symmetry, or if one has to break some of it and then make sure that we still get the correct answers. So it's still work in progress. And then the next thing we'd like to do is to add boundaries. So there are two types of boundaries that are interesting to study here. And so you can add boundaries with direct boundary conditions, and then in the gauge theory, that would correspond to just Wilson lines that are at some fixed positions. And again, the Wilson lines for this pure Engels theory are known for every configuration of the Wilson line, and in particular for configurations also where it's lead to singular worldsheets, like again, a figure 8 Wilson line, where the worldsheet changes orientation here in the middle, and we should get the correct answers also for worldsheets like this, which are not covered by the usual holomorphic mappings. So that's the next step is to see that when we add boundaries with the Rochley boundary conditions, we correctly reproduce those. And then if that works, then the next stage would be to add boundaries with non-boundary conditions, and then that should really give the Tuft model, where we have dynamical quarks at the boundary, which it should be possible to add them either for bosonic quarks or for fermionic quarks. And in the fermionic case, that should give us the Tuft model. So again, so assuming that this worldsheet is correct, I mean, so there are many subtleties in all the computations here, but once we add these boundaries, then we're going to have a very sharp set of predictions because this theory with the correct boundary conditions should just correctly reproduce the spectrum of that model on the nodes. I mean, so we don't have any free parameters here to fiddle with, so we should be able to see that once we add these boundary conditions, we get precisely the spectrum of the TÜV model, even though, of course, that's not put in any sense here. So that's the main consistency check that we're going to have on this approach once we add boundaries. And then on top of that, once that works, we'd like to also add these extra massive particles on the worldsheet that would correspond to adding extra massive adjoint fields in the gauge theory, as I described in the second part of the talk. So then that should connect to the second part of the talk, and we should be able to see that by putting together what we have here and what we have in the previous part of the talk, we should be able to get a consistent picture of the string dual of all of these theories that have adjoint particles. So all of these things are in principle straightforward, and that's why I think that this does give a systematic way to construct the string duals to all 2D gauge theories. But again, in practice, of course, there are many subtleties in doing all these steps. I mean, but I hope that we will be able to do all of them. I mean, there are obvious obstructions beyond just the technical complications. Let me just end with 3 more speculative directions that this could lead to. So if we could add these massive particles when the mass is large, then one could hope that maybe one could also go to low values of the mass. So for low values of the mass, there are many other interesting things. I mean, that's already mentioned. I mean, you have supersymmetry, then when the mass goes to 0, we get screening instead of confinement and so on. So in principle, all of these things should follow from these string theories, but of course the worldsheet theory of these particles becomes strongly interacting when we go to low mass. So the question is, will we be able to solve that worldsheet theory or not? So that's not clear. Another thing that would be nice to have is some holographic interpretation for these string theories. So a priori, these string theories are written just as theories in 2 dimensions. I mean, we don't see any obvious holographic direction appearing here, but we expect that at least when we add the dynamical particles in adjoint and so on, we expect that we should dynamically get some extra dimension and get some holographic interpretation, but it's not clear yet how that will happen. And last but not least, it would be nice to be able to draw some lessons from this for also constructing the string dual 4D gauge theories, either when they're weakly coupled or when they're strongly coupled, but I don't have anything to say about that so far. So thank you.
Sorry, but what's the advantage of having a string description? Because the other ones seem to be pretty good and give you already a lot.
Well, so and the other one, which one? I mean, just this Taylor formula. Yeah, it's that. But that, of course, gives us things that we already knew. I mean, the idea is that if we have a local worldsheet description, then we could add the boundaries and so on, and also add extra things so that we could get also other 2D gauge theories. I mean, so when we add boundaries, we get a worldsheet for the TÜV model, which is, it's not obvious how to get that from here. I mean, formally, you can sort of get it by taking the Wilson lines and then doing a sum over all possible Wilson lines with all possible configurations. That's sort of one way to write the theory with quarks, but that's a very complicated thing, of course. And here we hope that you can just write it as this worldsheet with boundaries, and that would give the TÜV model. And similarly, adding adjoint particles in this larger limit, it seems like it's, if you have a local worldsheet action, then there should be a prescription for how to do that, and that we don't know how to do by any other way. So the motivation for going back to this 2D angles is not to solve 2D angles by itself, of course, that's already been solved, but just to find a local description that we could then use for studying these other 2D gauge theories.
Would you say you have a general prescription on how to deal with integral over these modular spaces that would produce W in general?
Yeah, no, we don't. Yeah, unfortunately, we don't have any general prescription. So far, we just analyzed examples, and I mean, there is for the holomorphic case, there is a general prescription for how to deal with these singularities. So there you just get these orbifold singularities, and there the prescription was just to remove all the fixed points of the orbifold, and that seems to give the right answer. But there's no known generalization of that to this more general context of holomorphic and non-holomorphic mapping. So yeah, so I don't know. Yeah, so far we're just doing it case by case.
So it's unlike in the other better understood localization context where there's a precise way to deal with this, singularity in the modular space that you're integrating some counter prescription.
Yeah, well, I'm not sure. Like even in smallest Weizmann theory or something, is there a prescription to deal with all the smallest singularities that's completely
exactly? I don't know, yeah, but like the usual Negrasov function, we know how to deal with that. There's
to just smooth them out. Yeah, right. But so I don't know any analog of that here. So but yeah, but it would be interesting to find one.
Yeah, I think I missed it. You said this works only for the zero tension limit?
Yeah, the specific action describes the zero tension theory. I mean, so the zero coupling limit. And yeah, so to
because
describe the finite
that's
coupling
because
theory.
the tension thing drops out in localization now quantities.
No, yeah, oh, yeah, the tension that, yeah, so, well, the tension part would be the lowest component of this, but that's not in action anyway. We have here this integral d to theta, so so from the start we don't have any tension term. I mean, it's just.
But there is a parameter there, that's what I'm saying.
Oh, this parameter t, yeah. So because localization, the action is just independent of this parameter. Yeah,
True,
right. So this just vanishes, and yeah,
So,
the action is
so
independent
then
of
do
t.
you have a prescription to, or an idea of like how to reintroduce the tension?
Yeah. So well, we have one prescription, but we don't like it, so that's why we're still around it. So one way to do it is to So one way to do it is just to add the lowest component of this. So you can just add lambda times the lowest component times the same thing, just without the d to theta. So of course that would reproduce the right thing, but that breaks this supersymmetry and so on. So then we don't have localization anymore. And so formally we can add this term and then just take t to infinity, and then you would still localize just to the space of solutions to the equations of motion. And so formally that gives us the right answers, but it's not very aesthetic.
Doesn't that also just be degrees of freedom?
Sorry, yeah.
Don't you just do degrees of freedom because it's engaging variance?
Basically, the product of the Liouville mode, right, becomes.
No, on the worldsheet, I mean, we're certainly not breaking the worldsheet wild invariance or diffeomorphism invariance or anything. I mean, so yeah, this is still, you don't add any degree of freedom on the worldsheet. You're just losing some of the symmetries. I mean, these aren't gauge symmetries or anything. I mean, they're just, so I don't think we're adding any. We don't seem to be adding any more degrees of freedom. I mean, but we're just losing this localization argument. I mean, so once we add this term naively, you get contributions from all the different mappings and so on. And one way to get the right answer is to add this term, but then also just by hand to take t to infinity. And so in the supersymmetric theory, everything is independent of t, but even without the supersymmetry, we can just by hand take t to infinity, and then you would localize just to the extreme of this term, which would be still the external area mapping. So if you add this and do this, then you get the right answer, but that's sort of very formal.
But in the conformal gauge, it looks like now you have two bosons, right? So
No.
because you added normal Polakov term.
Yeah, but you also have the Versor constraints as usual. I mean, that's
what sets the central charge to the right edge? So you're saying the central charge is independent of?
But yeah, the central charge is just zero, and yeah, that doesn't depend on this. I mean, central charge is just zero because of cancellations between the bosons and the fermions here. I mean, that remains true whether or not you have this term. That doesn't really matter.
Why they cancel the central charges? Not why they add bosons and fermions. So one fermion is 1/2 a boson. So why now?
So this auxiliary P funny term.
Right. I mean, these don't obey the usual spin statistics, and these are sort of like vectors in space time.
I guess you're saying in
I mean, like the energy moment. So these are like fermions. These are anti-commuting degrees of freedom. I mean, but they, again,
so these are commuting worldsheet.
Well, they're not commuting because these thetas are anti-commuting, so they're anti-commuting, but they give rise to negative central charge if you just complete the two-point function of their energy momentum tensor.
But why again? Because that's
Yeah.
not true for if I just write exactly that expression for Minkowski space, I will get that they add right. Every fermion is 1/2.
Yeah, but that's because they don't have the standard kinetic term. I mean, their kinetic term is like quadratic in derivatives. It's not the linear in derivatives quadratic kinetic term. So they have their kinetic term is more like the kinetic term of bosons, and then you find that their computation, they don't have to go with each other. I mean, their derivatives of the other, you find that they give a negative central charge. So again, so that's independent of adding this term. But yeah, but so far we don't have that. We hope to find a better prescription to do this, but we're not sure yet.
So that's the only action, the only term in the first term.
Yes.
It doesn't look supersymmetric, but
Well, supersymmetric by definition, just because we have the central value to theta, but yeah,
but you have
when
the
you write it in
derivative.
components, then one component would be this b mu box x mu, and then there would be
But you have the derivatives
some
that way.
chi and
You have the derivatives that way, not the super covariant, the super derivative. But you say it's the same thing, it doesn't matter.
yeah, just like the usual Polish reduction. It is just the usual Polish reduction in superspace. So it has this, and this, so again, this is all of these x's are superfields again, so all of these things should be expanded in all the components and so on. It's just a standard Polish reduction in superspace. But it doesn't look like the usual bosons and fermions on the worldsheets. I mean, none of these have kind of standard kinetic terms or anything like that. You would get,
So this is central charge 0, but if you add the ghosts, doesn't it?
Well, the ghosts also cancel. I mean, so
You mean
so
because of
first
the
if you Yeah, so if you fix the conformal gauge, then yeah, then you'd have the usual BC ghosts, but you'd also have their fermionic partners. I mean, so they would also like sit in, each of the BC ghosts would also sit in some superfield of the supergroup present invariant. And for each of them, the bosonic and fermionic components of the superfield just cancel out. So it looks like this does have equal 0.
So even the ghosts have a non-standard kinetic term.
Yes, I think that's right. Yes, I mean, it's, yeah, it looks like a standard kinetic term just in this superspace with this integral beta theta, and that gives gives the connection with this expanded components. That's what it is. Yeah, but again, of course, you don't have to go to conformal gauge. I mean, nobody forces you to go to conformal gauge and normalize this in various other gauges as well.
Tengo per lenta.